Okay, so today we're going to be talking about the Hardy-Weinberg equation, which is a really useful equation in population genetics for determining allele frequencies within a population. And if we have a simple dominant recessive phenotype relationship between the two alleles, it's relatively easy to figure out what the allele frequencies are within that population. And like I said, we're using two alleles, which is probably the simplest kind of Hardy-Weinberg problem you will ever come up with. And here we're going to be using the big R, little r type of notation that we are accustomed to using when we first start learning about Mendelian inheritance, when we first start taking genetics. I figure that's pretty easy for everybody to work with. And instead of the color and shape of peas, here we're going to do human hair color just to mix it up a bit. So out of a population of about 100, we're going to say that about 20 of them have red hair. Now, if you remember, red hair is a recessive trait. And as a recessive trait, you have to have both alleles. You have to be homozygotic for the trait. All the other members of the population must either be homozygotic for brown hair or they're heterozygotes who are carriers for red hair. They have one red allele, but because it's a recessive trait, they still end up with brown hair. So, if we look over here at the Hardy-Weinberg problem, or the Hardy-Weinberg equation, excuse me, the q to the power of 2, q squared, this is going to represent those who are homozygotic, and we might be low on space here, so I'm just going to say, let's see, homozygotic red. Homozygotic red. This number over here, this p squared, that is going to represent homozygotic brown. And let me move this over here. And the number in the middle, the 2pq, those are going to be the heterozygotes. The ones who are brown but are carriers for the red hair gene, or the red allele. So that middle number there represents the ones who well, the middle number plus the first number, the p squared plus the 2pq, those are going to be all the brown ones right there, all the brown-haired individuals. So to break this down, for the time being, we're going to ignore this 980 over here, and we're just going to focus on the 20. Okay, so 20 out of 1,000. What's 20 out of 1,000? That's the same as 2 out of 100. So that's 2%. 2%. So 2% is 0.02. All right, so how do we find q? Well, we have to square it. So we have to get out the calculator, put in 0.02, go ahead and square that, and holy crap, that is a long number, a long small number. So, okay, we're just going to go ahead and round this to 0.14. 2 significant figures is good enough. So Q is going to be 0.14. And here, your job can be made a little easier if you remember that P plus Q must always equal 1. P plus Q must always equal 1. Or, yeah, so what we're going to do is we're going to take 0.14 and we're just going to subtract that from 1. And that should be 0.86, but just to make sure, we're going to do it in the calculator. So 1 minus 0.14 equals 0.86. All right, so P is going to be 0.86. And here we could just square this right now and figure out what the P squared is. So 0.74, we're going to say 0.74. Or we could actually figure that out later once we have the 2PQ filled in. So I'm going to go ahead and delete this so we can do it both ways and figure it out later. All right. So we've got the majority of the problem solved here. All we have to do is take 0.86 and multiply it 0.86 times 0.14, and because both of those numbers are less than 1, you know that the answer is going to be smaller than either of them. So 0.86 times 0.14 equals 0.1204. So we're just going to call that 0.12. 0.12. Actually, can get rid of that there. 0.12. And if we multiply that by 2, we are obviously going to get 0.24. And actually, I'm going to move that a little bit, 0.24. And what does that give us? Well, that gives us something. Well, we already know from before it's 0.74. I'm just going to assume that we still have the P2 in there. Let me put it back just to make sure. 0.74. Plus 0.24 plus 0.02. And let's see, let's plug that into the calculator. 0.74 plus 0.24 plus, let's see, that's 0.98. We already know what the answer is going to be. It's going to be 1, which is exactly what we need in the Hardy-Weinberg equation, because it's always going to answer, or it's always going to be 1. The answer is always going to be 1. So that works out perfectly. Now remember how I said a moment ago that we could figure out the 0.74 at the end? Well, we can do that just by adding the 0.24 plus the 0.02. So let's just do that real quick. 0.24 plus 0.02, which is obviously going to equal 0.26. And then to figure out what P2 is, to figure out how many are strictly heterozygous for the brown allele, then we would do 1 minus 0.26, which, if you can do math in your head, you've probably already got the drum roll going in your head. Let's see, 1 minus 0.26, is it going to be 0.74? Yep, 0.74. And so the math works out perfectly. All right, let's try another problem. Okay, so basically we're going to do the same thing again, except we're going to use eye color. And this time we're going to say that out of a population of 1,000, about 30 of them have blue eyes, and 970 have brown eyes. Okay, well, 30 is, well, that's 3% of 1,000. So, first thing we're going to do is over here in our q squared, we are going to plug in 0.03. And we're going to do the same thing we did before to figure out q. We're going to put in 0.03 and we're just going to square it. Real simple. Another long small number. We're just going to call that 0.17. 0.17. All right, so what is 1 minus 0.17? That's 0.83. So we know that P has to be 0.83 because P plus Q is always going to equal 1. So P has to be 0.83. And just like before, we can solve for P squared right now, or we can do it a little later. It doesn't really matter. I think it's easier to do it right now, especially if you have a calculator on you and you've already figured out what your P number is. Then you just, click square and it's real simple. So 0.69. 0.69. All right. So, again, really simple. P times Q, 0.83 times 0.17. 0.83 times 0.17 equals 0.1411. We're just going to call it 0.14. 0.14. And if we multiply that by 2, that's 0.28. So, what does that give us for the problem here? If we plug in the numbers, that's okay. Our P squared is 0.69 plus 2PQ which we've determined is 0.28, plus q squared, which is 0.03. Plug that into a calculator, and if we're right, that will equal 1. So let's see, 0.69 plus 0.28 plus 0.03 equals 1. So we've determined that in our population, 0.03 or 3% are homozygotic for the blue allele, 28% are heterozygotic for the blue and brown alleles. They're carriers for the blue-eyed gene, and 69% are simply homozygotic brown-eyed. And so there you go, the Hardy-Weinberg equation, really simple with two alleles that have a simple dominant recessive relationship. Obviously, when you start getting more alleles involved and you start dealing with incomplete dominance and codominance and whatnot, it can all get more complicated. But this is the easiest way just to learn the fundamentals behind the Hardy-Weinberg equation with regard to population genetics. And so there you go. Don't forget to like, comment, and subscribe to my channel. Thank you very much. And oh yeah, I've got to plug my website while I'm here. https://djohnscott.com, which is mostly my art website nowadays. And I'm also the webmaster for genesispanthesis.org, which is my science website. Well, it's not my website, I'm just the webmaster. But that's where most of these videos will eventually be available. So yeah, thank you very much and have a good one. Peace.